Hey physics class, I've got something a little different for you today. I've got something kind of like a riddle I'd like you to solve. I call it Stars Are Impossible. So here's the situation we're starting off in. I've got a cosmic cloud of hydrogen gas in space. Thinking about it in terms of the ideal gas law, it's got some pressure, some volume, some number of moles of hydrogen, and some temperature. It doesn't really matter what they are. All that matters is that they're going to change, because nothing ever stays the same. These hydrogen atoms are all attracted to each other by gravity. So, given enough time, eventually, they will collect together. So, what's changing here? It's not like there's molecules escaping or being added, so the number of moles is staying the same, but the volume is decreasing. As gravity condenses this cloud, the volume decreases. Now, volume is directly proportional to temperature. So, is it cooling down? In space? It was already about as cold as it can get. Well, the pressure must be going up then, right? Because pressure and volume are indirectly proportional. But if the pressure was going up, it can just push them back out. So the question is, how can this cloud of hydrogen gas ever collect down to the point where there's enough pressure to ignite fusion in the core? So here's a solution for you. I mentioned that the temperature could be going down in order to make the volume decrease, but that's clearly not an option because out in space, the temperature is already so low that it doesn't really have anywhere to go. And if the volume is going down, then the pressure is going up. But remember that all of these variables interact with each other. So the pressure going up can also cause it to heat up. Now, the pressure can be relieved by expansion, but the expansion is being counteracted by gravity. So the question is, what is counteracting a change in temperature? Nothing. So if the volume goes down and the pressure goes up, pressure, P, is directly proportional to the temperature. And that means that as the pressure goes up, the temperature goes up. But that is able to escape by radiation. So as the pressure increases and the temperature increases, this is able to lose heat by radiation. And that's how the energy is able to leave, not through a release of pressure, but through a release of temperature by radiation. And it can get to the point where the pressure is enough to start fusion. Hey, so I was finishing up editing the solution video to the Stars Are Impossible problem, and I was a little bothered because I left out a couple details and I wanted to make sure that I included them. So first, if you look back in the notes for the ideal gas law when I first gave it to you, I mentioned that there were a couple of assumptions that applied to it. There were infinitely many, infinitesimally small, uniform particles that don't interact with each other. Those are the conditions under which the ideal gas law is supposed to apply. Well,
guess what? If you have a whole bunch of particles that are all attracting each other by gravity, then that breaks the assumptions. Those are particles that interact with each other. So, right there is just an indication of how the ideal gas law isn't even technically the right equation to use for this. It does still matter. Pressure and volume and temperature still have those relationships with each other. It's just that that equation can't perfectly describe the situation. Okay, so besides that, so if you've got a a cloud of hydrogen gas, just picture like you had a gravity switch where you could just like flick gravity on and off, right? So let's say you've got your cloud of hydrogen gas. Gravity is off. The ideal gas law applies. PV equals nRT. Everything is staying the same. Everything is in equilibrium. As soon as you flick the switch on, gravity is on. All of a sudden, pressure has increased because there is now a force that was not there before. This pressure is going to have an effect on the volume and also on the temperature. The gas is going to compress slightly, get smaller, and also heat up. It will do both of them. Those changes are in opposite directions, obviously, so they would only go so far. It's just that the volumes change is going to just end up being stuck. There's going to be a balance. But the temperature change is the one that is not going to be in balance, because you can't lose or gain volume by radiation, but you can lose heat by radiation. So you turn on gravity, the cloud of gas compresses slightly, heats up, but it's able to cool off by radiation, at which point you can basically just start over, and the pressure causes some compression. The temperature goes up, the heat is lost by radiation, and so it can continue to compress and compress, all the while being able to shrink because heat can radiate away. So if you were to watch this happening, over a long period of time, you would be able to see, if you could see in like these, infrared wavelengths, you'd be able to see it glowing hot as it's compressing because of all the heat that it's shedding. Now, again, we're going to have the ideal gas law not properly describe things, because once you get to a certain pressure, then they're going to start interacting with nuclear forces instead of physical ones. But that was outside the scope of this problem. This was just about how, if you've got pressure from gravity and volume decreasing from gravity, how are you going to get rid of the energy? You can think of gravity as doing work on that cloud of gas. That work can be expressed in terms of a change in pressure or a change in volume or a change in temperature. And depending on what container it's in, one of them will be held constant. Like, for example, in the hot air balloon, the pressure and the volume were both held constant. Or in like a heavy metal tank, the volume will be constant, but the pressure and temperature can change, right? So in the case of just a gas free in space, nothing is held constant. Everything can change. That's part of what makes it complicated. I think I got everything in there. Yeah. I just wanted you to be able to have in mind the direct and indirect variation relationships between pressure, volume, and temperature, and see if you could figure out how gravity could do work on this cloud, put energy into it, but then the energy just leaves so that gravity's in a position to do more work. Okay, well, anyway, just wanted to make sure that was in there. Yeah,